Okay, so the takeaway is I want to show you how to effectively use this GPU instance that you set up. I've left a couple of steps off on automating setup of a remote GPU instance. And the biggest thing that I've left off is how to set it up so that your setup.shell script runs automatically when your machine starts. So on Paperspace, there's something called a pre-run.shell file. And so Paperspace, I believe, will run bash rc, and then it will run your pre-run.shell file on startup, or maybe it just runs your pre-run.shell file. But it only does it when you first start a machine. And so inside of your pre-run.shell file, if you put /storage /config /project4 /startup.shell, it will start the machine and automatically run your configuration script. And you don't have to do any of the stuff that I'm about to have to do, meaning you don't have to do run your startup.shell file. Like, you don't have to do this because it's automated. So storage. Actually, I don't know where I put this. Let's see if I can find it. So I don't know if I have it. Do I have it in Project 4? I don't know if I do or not. Setup.shell. Let's see. I don't think there's anything in this file. And bash history, local Kaggle, installing my packages. I can't help but to think that this is not working the way that I want it to work. Okay. And yeah, it's not working the way that's not the one that I wanted to run. So, okay. Where did I put it for this class? Let's see what I got here. Maybe it's in my config folder. I think it's here for me. All right, let's see if this works. I think that's right. Okay. So what I've just done when I ran this other setup.shell from PCSE 595, I think what I did was I reinstalled some other stuff to the Python user directory somewhere. So I think I'm taking up a lot more of my storage space on, well, you only get 20 gigabytes of storage on a Paperspace instance for free. So I think I just installed Fastai AI and Tim and PyVinyl to some bogus location. I'll have to unroll that later. All right, so I think everything's configured and I'm ready to roll. Anyway, that's setup.shell script. If you put it in pre-run.shell, then Paperspace, when it starts, will run it automatically for you. Let's see if this is configured properly. Yeah, and I look kind of golden here. That's all set. All right, so let me go back to I'm going to go back to notebooks. And I don't see any notebooks here. Okay. All right. So in that case, so I am in the complete. So what that means is I'm on the wrong instance. Okay. So let me go find where the right instance is. This thing is sitting in a. Let's see. I think I made some changes to it. PCSE 595 code. All right. So let me pull that. I'm going to find this repo. I'm going to clone this, and I'm going to go to my Paperspace instance here. And I guess actually, I want to clone this in my notebooks folder. So it's going to appear over there. Okay. Let's see if that's going to appear now. There it is, PCSE 59. Okay, now we're set. Now I'm back to Kaggle, Patty. All right, so what's going on with this now? Unhandled error. I have no idea. Let's go over here and check it out then. Kaggle Patty, IPy, and B. That looks right. Let me make sure .local is set up properly. Oh, I know what I did. One of the reasons why I just mentioned that you want to run setup.shell first before you do anything else. One of the reasons you want the system to automate it for you is if you happen to open a notebook, then what's going to happen is that notebook is going to write its temporary contents to local.shared inside of here. And it looks like I haven't moved my local folder here. And so what's happening is I think I've got a symlink to .local somewhere that this thing is finding when it should be looking in another .local folder. So, and the only way that I know to get around this is you got to stop your machine and start it again. All right, so let me go back to Paperspace. And I lost my original link to it. So I'm just going to go stop this machine. And I think it's looking like I'm running on a different machine. So I'm going to stop this one. And I'm going to go back to my projects. And I think it must be, it's here that I'm working. Let me open that one up. And so I'm going to start it up. I'm going to run my setup.shell. So everything, my notebook should work fine once I get this up and running. Okay, there we are. Okay. All right, before I mess with any notebooks, I'm not sure where it is. And so if I had put all of this, like I said, in a pre-run.shell script, I wouldn't have to go through all this trouble of finding my setup.shell script every time. Let's see, ls. There we go. Setting up Python packages, making sure they're there. Okay. Going back here. I still have a local folder. What happened there? My local folder is supposed to be symlinked, and it's not. Something's not quite right in my setup.shell. And I'm not sure why that is. All right. However, that's just because I was messing around in my setup. Let me go check out my Kaggle folder. I don't go from there. So anyway, I'm beyond. I've already talked about getting your setup shell working properly. So I kind of wish I didn't pull back the covers and show you how messy and multiple bits of garbage I have on my machine, because I was just jumping all over people about that. And then you see my machine, it's just the same. Anyway, you're going to find that we're all guilty of that. And I think me more than others. All right, so this is the notebook we're working in. This is the competition we're working in, Patty disease competition. Once you accept the terms and conditions of the competition, you can actually download the data. You don't download it through here. You download it using this. And that's what I'm showing you here. So I'm going to use the Kaggle command line interface for that. So if it's not there, this little bit is very similar to set up Python packages. The little bit of the Python file that would automatically install Fastai and Tim if needed. So I'm going to run this, and it's already, actually it's not there. Oh, the reason it's not there is because I didn't set up a local symlink. Oh, I was supposed to go back and add that. Right. So I've got basically a brand new local. So I've got to install this every single time. All right, but no worries, it's there now. So I've got my, I've got everything. I've got my Kaggle command line interface set up. And do I have my Kaggle key? Good. I've got my Kaggle key here as well. So now when I try to get this data, now I've got to figure, where do I want to download this to? Right now I'm running this in /notebooks. If I run it in /notebooks, it's going to download all this stuff and it's going to plunk it inside of my notebooks. But right now it's going to check, hey, does train directory exist? And train directory is ./train images. It does. So if that exists, then it's not going to do any of this stuff. So because it's already there. You can look inside of train images. I think there's 10,000 images and there are 10 categories. And within train images, there are 10 directories. And each of those 10 directories correspond to one of the diseases. So for this one, bacterial leaf blight, every one of these images in here have bacterial leaf blight. And this is just a way to organize your data so you know what these images correspond to, what the actual target disease should be for each of the images. And that's going to come in handy for a minute. Now I got to this point where I just actually loaded this file, train.csv. I've got a CSV file that shows me what all this information about all of these images inside of train images. So for this image, it's in bacterial leaf blight 100330. So I can open up train images, open up bacterial leaf blight, and I can find 100330 in there. So I can search 100330. Yeah, there it is, sitting right there. So I can find all these images in there. That's the image. That's the directory it's in. That's also the label for it. This is useful information, but in order to actually use this information, we've got to make a custom optimizer, a custom data loader, and we have to have a custom head on the model. And we're not going to do that in this class, not in one day anyway. The data set's unbalanced. That's what this is going to show us. Mostly normal and roughly a fifth as many bacterial panicle blights as normal. And I've got a bunch of these blast problems. So apparently this seems to be a common disease for rice. So my guess is my model is going to be pretty good at recognizing blast and pretty good at recognizing HISPA, whatever that is, pretty good at dead heart, pretty good at Tungo. But the further down you go, the less good it's going to get. It's going to be less so at this one, less so at leaf blight, leaf streak, and panicle blight. It's just going to not going to be as good because it doesn't have as many examples. We could balance this data set, and I talked about that earlier. We can use a weighted data loader, but that's beyond this class. So first thing you need to do is, well, make sure these images are the same size. And so what I'm going to do is I'm going to run this bit of code here. And what this is going to do is it's going to go through every one of the files. So I'm importing this parallel library. And this is from Fastai. And this is what this is all about. Fastai is a library that wraps PyTorch functionality. And it takes a bunch of complex PyTorch stuff and it wraps it up in a simple API call. So this little chunk of code, what it will do, it also has a lot of other helper functions that are part of it. And some of these helper functions will go over here. Some of these helper functions, here we are. They're there to make it easier to do deep learning. On computer vision, on textual data, on tabular data. That's what the functions are for. And this is one of them. So this is a parallel processing library. And so what I'm going to do is I'm going to fire open a separate terminal, and I'm going to show you what happens. I'm going to, let's see. apt install htop to apt get install. Did I get this right? HTTP. Okay, I'm spacing apt get htop. Oh man, I'm totally spacing on it. Is it apt get install? Oh, why did I forget what this is? All to get htop. Come on. All right, it's there. This is just going to show me what's going on in my machine. My machine has 8 processors right now, and they're not running they're not doing a whole lot. This is all the processes that are running. This is a very lightweight machine. It's not running a whole lot. Let's chunk this over here so we can, down here, so we can see what's happening. So still not doing a whole lot here. So what this is going to do, it's going to import a parallel processing library. I've got this function that I want to call, this get image files. Get image files will go through my train directory, and it'll recursively search through my train directory and pull every image file in the directory that it's in. And it's going to generate a list. Now, what I want to do is for each of those files, I want to see which size it is. That's what this function does, simple function. It's going to take that, whatever that file is, it's going to open it as a pill image, and it's just going to get the size of it. It's just going to get the size of the image. And then I'm going to run this parallel function here. That's what I'm using from FastCore Parallel. It's going to parallelize this. It's going to launch 6 separate threads, and these threads are going through multiprocessing, so they're not beholden to the global information log. It's going to take that list of files, and it's going to take that function, and it's going to generate, and that function is going to return the size of each image. And then I'm going to get this list of the sizes of all of my images. And then I'm going to convert that to a series, and I'm going to get the value counts. So when I run this, what's going to happen is you can see all of these threads are running. And so I'm maxing out all of my cores. I don't care. I mean, CPUs aren't as big of a deal when you're doing deep learning. CPUs are a big deal when you're doing pre-processing of the images before you send them over to the GPU. And I'm pre-processing images right now. It's running. There's 10,000 files to go through. So this will take a sec to run. Not too long, but a little bit. As soon as all these lines go back to basically their quiescent stage, that means we're finished. And so when it finishes, we're going to find out that we have 4 images that seem to be flipped. It's got to finish. Okay, it's done. 10,403 images that are 480 by 640, and then 4 that are 640 by 480. Now, the thing that you might think is, all right, there's just 4 of them. Why don't we dump them? We could do that, but I've got this data set that has train images there, but I've also got test images, and these are the images that I'm going to go through, and it's trying to show me all these test images. It's taken a while to print them out. You see this inside of this folder. There should be test images. I don't see any test images. Train images, got a ton. Test images. They seem to be missing. I might have to go and get them. So inside of my test images, there's probably also going to be some that are flipped. So I don't want to just get rid of these. What I want to do is just resize them all to be the same size. And so that way, when I train my model, well, it's just going to resize them all. And I get to use those 4 extra images. You never want to get rid of data. All right. So the way deep learning models work is you basically have one of those TIM models, and it's a convolutional neural network. You feed it images. Hey, this is an image of rice that has bacterial leaf blight. This is an image of rice that's normal. This is an image of rice that has blast. And you just keep giving it picture after picture after picture, and it eventually configures itself so it can recognize different diseases. But in order to feed those images, you need to, well, you have to, let me move this over. Let me make that a little skinnier. You have to have some component that's going to load the data. And the data loading is done with Fastai AI using data loaders. And a data loader will consist of a data set, which is the data, all the data itself, and then an iterator that will iterate through that data set. And that's what the data loader does. So I've got 10,000 images. And I think you've heard, if you've had a deep learning class, you know how long it takes to train these models. Or you've probably heard that it takes a while to train a model. But if you're experimenting with stuff, what you want to do when you're not really sure that you're on the right path is you want to speed things up. The best way to speed this up is to subsample your data set. And that's what I'm doing here. What if I just use a smaller sample of my data set instead of a larger sample? That's what this will do. So if I want to, right now my data set has 10,407 images. This command will pull out, will create a data frame that just has 500 images. And you can see, there's my data frame. It has 500 rows and 4 columns. I have 50 samples of each of those diseases. And if I use this data frame, and I'm trying to train a model, that model is going to train very fast. I'm going to see if it works very quickly instead of waiting a long time to see if it works on the real data. And I'll show you the difference in a minute. All right, so here's how I would make a smaller data set. Here's the data loaders that I was telling you about. Remember, this is what feeds my deep learning model all these images. Notice it's pretty straightforward. FastAI has a lot of different ways to create data loaders, but the two that I'm going to talk about are you can create it from a file system or you can create it from a data frame. You notice the file system here is set up so that my train images, inside of train images, I have all of these other folders that are full of the diseases. So if I'm going to create an image data loader from the folder, I just tell it where my images are. I tell it how to split it between train and validation percents, because you guys have covered that in this class or in previous classes. This says 80% is for training, 20% is validation. Batch size is the number of images I feed to my model at a time, and that's defined up. I've defined that up here. Where did I put it? Here, there's my default batch size is 64. I'm going to feed my model 64 images at a time. And then I have these transforms. This will resize every single image on the CPU to 480 by 480. And what Squish will do is it's going to take, if it's 640 by 480, it's going to squish it all down. So which means the aspect ratio is going to be screwed up. I can crop, I can squish. There's several methods I could use. I'm going to use Squish. These batch transforms, they take place on the GPU. I'm going to resize it again to 128. And I'm going to have this scale factor as well. None of these are important right now. These are defaults. And I can show this for a data loader. Once I create a data loader, I can show a batch of data. Batch size is not defined. Did I not hit that up here? Oh, here it is. Now it's defined. There we are. Give it a minute. It's going to, once this image data loader is created, it's going to show a batch of data. And so there's a picture that shows rice that has dead heat. This has tongue grow. This is, I don't know what any of these things are. And that's kind of one of the cool things about deep learning. You can just throw these models, as long as you have training data, you can just throw the data and the model together and let the model learn how to recognize the differences. You don't really need to know the differences, although it really comes in handy if you know a little bit about the field that you're working at. So this is just 9 images, which illustrates some of the diseases. And this is randomly sampled from the 10,407 images. And so I'm going to see probably, I should see more normals than anything else. Probably more, I'd imagine more dead heats as well. How many dead heats are there? There's normal, there's blast. There's a lot of dead heats. I expect to see more dead heats, HISPAs, blast, and normals than anything else. So dead heat, HISPA. And I did get one of the blights. So, but this is all luck of the draw. That's a batch of the data. I can also create a data loader in a different way. I can create it from a data frame. Now I've got a data frame. I created this data frame up here. Here, I loaded the train.csv file. This has every image, every location. So, but I need to have a little more data. I need to have the image name and where it's located. So what I'm going to do is I'm going to modify, I'm going to add an extra column. So I'm going to add my label and my image ID. And so when I run this, I'm going to wind up with this extra column that says load. This is where this particular image is located here, bacterial leaf blight 10030.jpg. And now all I have to do is also call image data loaders again from data file, data frame, give it the data frame, give it the path to the train directory, which is basically the train images. The column that shows where it's located is column 4, 0, 1, 2, 3, 4. The column that shows the label is column 1, which is right there. And I'm not going to add a suffix because it's already there. It's JPEG. The folders start from where we are now, which is in notebooks. Batch size is equal to whatever the batch size was. And then I set up my validation percents of 0.2, and then my transforms, my CPU transforms, and my GPU transforms. And so this will create, and notice how fast it is, how fast it was to create that data loader. This is much faster because I'm pulling it from a data frame as opposed to creating this data loader. This data loader has to iterate over the file system to generate its a data loader. This one, all it has to do is iterate over a data frame. So it's much faster. All right, so now I'm going to clean up my memory. Another thing I want to look at is I want to always be aware of what's happening with my GPU. So there's a command called, which tells me what's happening on my GPU. But unless I keep typing that over and over again, I mean, I'm just going to get a snapshot right now. But what you can do is this. You can watch it. And I think I mentioned this on Tuesday. So now every 2 seconds, that's going to update it. Right now, I'm using 1.3 gigabytes of a 16 gigabyte machine. And I'm going to use one other tool. So I'm going to add another terminal window, put it down here. And I want to see, what my memory utilization here is. Now, this is a column that I'm very interested in. These are the symmetric processing units on the graphics GPU. So, but I'm mostly I'm concerned with memory utilization. I want to get the memory utilization up. And so, all right, I'm going to run report GPU. I'm going to clean up everything. I got a little bit of GPU memory back. And now I'm going to start using the TIM models. And TIM has, let's do this. Start with that. TIM has lots of models. So if I just do TIM list models without pre-trained equal to true, I think that is it. Pre-trained is equal to false. You're going to see that there's hundreds of models here. All right, but this little bit of these last 2 lectures are all about fine-tuning. Fine-tuning only works with a pre-trained model. Training a model takes hundreds of hours of GPU resources, generally. Fine-tuning a model takes minutes of GPU resources, but you have to start with the pre-trained model. So out of all of these models, let's see, how many pre-trained ones do we have? These are all my pre-trained TIM models, and there's still a ton of them. And so now you have to pick a pre-trained model to use. So go back over to, where was the how to pick it? I think it was, there's a ton of pre-trained models too. Best vision models for fine tuning. Let's open that up. Right here. I'm going to go down through here. I think this is on the pets, stuff that's trained on the pets. And I want something that's going to train fast, meaning the fit time is as low as possible. And I want the error rate to be as low as possible. So I'm looking at all these. These are looking pretty good. Like Comnex Tiny, that looks good because it trains fast and it's accurate. Comnex Tiny and 22K, that looks good too, because that's fit time takes a little bit longer, but it's a little more accurate. So either of these are going to be fine. And so I choose one of these models to use, because what I'm trying to do here is these models were trained on ImageNet, which has pictures of grass in it. So it's similar to what I'm trying to do, recognize pictures of rice that has disease on it. So that's why I'm choosing these Comnex Tiny models here, because they train fast and they're accurate. And this is a really big deal. Most of the time when you see people picking a model to train on, picking a model to use when they're doing some sort of inference, is they just pick ResNet. You don't do that anymore. You try to intentionally choose a model that trains quickly and that is accurate. That's what you're after. If you want the highest accuracy, then you don't worry about fit time. You just train a model that has the highest accuracy on the type of data that you're using. I want both. I want a low fit time and a low and a high accuracy. Comnex Tiny is going to do it for me. Any of these models are pre-trained, and I can use any of these. So let's load one of them. Comnex Tiny. So is that an actual model? I guess that is a model. FB and 1K. Let's see what that gets me. All right, it's downloading this model. Got the model. Notice it's going to automatically download it. Now notice, if you want to see what's going on here in this Vision Learner, there are two calls: Vision Learner with Comnex Tiny and Vision Learner with the string Comnex Tiny. So let's go look at the code base. And so one of the things about Fastai is it's kind of opaque in places. I'm going to put this. Can I put this one? No, it's not going to work well. Let's put it right there. There it is. Okay. Vim-T Vision Learner. So let's go and take a look-see at that. So here's my Vision Learner. I'm going to be right back. I need to get a power cord. My laptop has a habit of telling me that I've got 20 minutes, 20% left, and then it dies. All right, so here's Vision Learner. So you can fish down through here. There's the DataLoader I'm going to use. Here's my architecture. Notice, you can go down here. This is the sort of thing that I think is it's very opaque. Notice that Vision Learner doesn't have a lot of, there's not a lot of documentation here. I'm not really sure what's happening. Fastai has a lot of documentation online, but inside of the code, I would like a little more. So, for instance, the way that they determine whether they're going to use the original Fastai architecture or TIM model is they check to see if this argument here, that argument right there, is architecture, is a string or not. And they do it here. Hey, if architecture is a string, then they're going to load a TIM model. And if it's not a string, then they're going to let's see, if it is a string, they're going to load a TIM model. Otherwise, they're going to create just a plain old vision model. And you have to fish around in the code to see that. And you can actually go to these things to see how they differ. There's create vision model. There's not much to it. There's only if it's just creating a custom vision architecture. Go back, create TIM model, creating an architecture using TIM. And this is all about using TIM. So this is what we're going to do. We're going to be creating this model using TIM. I think it's a little hard to understand the Fastai code base quibble that I have. And that's a problem you run into when you have a wrapper API around a more complex API. And you're always going to have this problem. All right, I've got my learner here, so now I can work with it. So there's a couple of ways. Notice all I've done now is I've created a data loader. I've created a vision learner using a TIM model, and I chose my TIM model by going to best vision models for fine tuning and choosing something that trains fast and it's accurate. And got my learner. What I want is a low error rate. Now I'm going to, well, the class is about fine tuning, so I'm going to call fine tune on this learner, and I'm going to do it. I'll do it for 3 cycles. Now there's 10,000 images it's got to go through, so this is going to take a little bit of time. This is where using a subset of the data is really going to play off. So look how long this is taking. It's kind of tedious, isn't it? So let's, so let me kill that. So kernel, let me interrupt kernel, go up here. And of course, I'm probably going to blow the whole thing by doing it this way. And I'm going to create a new data frame. Instead of new data frame, I'm just going to call this df is equal to, no, I'll do it down here. Escape below. Df is equal to new df. Okay. And so escape below df. All right, so now I'm golden. So now I've got my data frame. I want to do this. Now I've got their location. So now my data set has gone from 10,000 rows to 10,407 rows to 500 rows. So I'm going to train faster. All right, did I create my data loader from data file? There we go. I've got it. And it looks like I'm using up a lot of memory right now. Let's get that memory, some of that memory back if we can. Where's my report GPU? Get anything back? Nope, that's okay. Because once we delete the model, we'll get, because we've sent our original data loader over. Actually, we've created our data loader. So what's happened now is when I created the data loader here, it's still on the CPU. When I create a learner with that data loader and I start to fine tune it, it's going to push it to the GPU. So this learner will replace that learner. And I'm going to use my data loader and I'm going to have a much smaller data set to work on. Now watch how fast this goes for fine tuning it. I've only got 500 images to train on. See that? See how fast it is? This is why you want to use a subset of the data when you're just testing to see if it works. What I'm looking at is my error rate and my validation loss. I want my error rate to go down, and I want my validation loss to go down. Validation loss is going down, error rate's going down. And so likely what I could do is I can fine tune this until it's perfect on these 500 samples. And I'm going down pretty fast. So let's see, 55% accuracy, 45% accuracy, 49% accuracy. If I did it for 3 more cycles, you get better and better and better. 48, it's just going to go down and down and down. Validation loss will keep going down. And generally you want to keep training as long as your validation loss goes down. As long as it keeps going down. Now, you don't want to do early stopping with Fast AI's learners. They have something called fine tune and fit one cycle. Fit one cycle actually takes the learning rate and it starts off very low for warm up. It ramps it up in over a cosine wave to the learning rate that you want after X number of epochs, and then ramps it back down. So you just want to, as long as your validation loss is going down, you're golden, and now it's starting to go up a little. And so now I'm done with this. So that's about as good as I can get. So for the 500 samples that I have, this is about as good as accuracy as I can get. All right, so let's go back and get the original, back to the original data set. Anyway, the whole point of that was to show you that, a way that you can speed up your training to make sure that your model's working correctly. And my model's working correctly. It was training, it was getting more accurate. All right, so there's got all that. Oh, I don't want to do this from DataLoader, from folder, so I'm going to interrupt kernel because it's going to take too long. And I'm going to go and do it from that. Create my data loaders from the data file. There we go. How much memory am I using? I'm using a lot of memory now. Kill that. Load my vision learner. And I want to fine tune probably we'll do it for 5 cycles. And this is going to take a lot longer. So the first number here is the batch that it's on. The second number is the number of batches per epoch. And so I'm doing this for 5 epochs. And it's going to take, 20, 30 seconds per epoch. To train this ComNext Tiny took hours to days on 1 or more GPUs. To train this network, it's going to take 3 or 4 minutes tops. When I'm done training, the accuracy is going to be, 95, 96% accurate, somewhere around there. So I'm going to let it go, and I'm looking at my GPU memory over here. And I'm looking for my memory utilization. So notice right here, my memory utilization is pretty darn low. So I've got this 16 gigabyte GPU, and I'm not using a whole lot of it. And these processing units, I'm not using many of those either. Those are also on the GPU. Well, right there, I got up to 99% utilization. That's not bad, but for the most part, I'm not using these things. First epoch, well, it's still working on it. First epoch, error rate is 0.29. It's 70% accurate, starting off with a validation loss of 0.87. And it's just going to keep going for a while until it's finished. When I'm looking at my amount of memory, I'm using 4 gig out of 16 gig. I've got 12 gig left. I'm actually training on this. Training is what's going to take the most memory. I have 12 gig left on this GPU. I could actually use that 12 gig for another job to run. But I'm going to have a bottleneck because of the system bus. Actually, I'll have a bottleneck for the system bus and for the GPU buses, internal buses. Or what I could do is I can increase my batch size. And so then the amount of memory that I use, so if I doubled my batch size, instead of having 130 batches per epoch, I would have 65 batches per epoch. And they all train in parallel. So basically this training cycle would be twice as fast. All right, so this is going to take a good little while to train. So it's going to train for a bit. I'm just going to let it go. And I'm going to be watching I know my memory utilization is okay. So if I increased my batch size, I'd get my memory utilization up more. So this particular situation with this GPU and this utilization of my GPU, I can actually increase the batch size. I could use more of my GPU. Increasing the batch size, all that's going to, it's going to have some consequences. It will allow me to train my model faster, but you're giving it more images at once, and you're trying to average out the error in those images. And so generally there's a rule of thumb. When you increase your batch size, if you double your batch size, you should increase the learning rate by the square root of the increase in the batch size. So if you double your batch size, you should increase your learning rate by the square root of 2, 1.4 or something like that. All right, so look what's happening. My error rate is kind of dropping like a rock. So it's now at from 0.29 to 0.20. My validation loss is still dropping. If my validation loss is dropping, that means it's not overfitting. And that's what you're after. You want to keep training until the validation loss starts to go up. Now, I think you've talked about this before. When the validation loss is going up, that means your model's doing something that's overfitting, which means that it's memorizing the data set that it's training on. You don't want that. You want it to kind of get the gist of what's going on the data set that it's training on. So when you show it something new, it can recognize what the new stuff is. It can take what it's learned from the training data set and it can apply those principles to these new images and come up with the correct answer. All right, so saving the model. If you get tired and you want to stop for the night, you can save it, and you can reload load the model. Now, one thing about this is you want to save the optimizer as well, because it will save the state of the optimizer as well as the weights of your model. And if you want to see what's going on here, I don't think I can get this until this thing finishes training. So epoch 0, it's training. I should have just had it trained for 2 cycles. This is going to take a while. Yeah, I might change this a little bit. So this will take too long for this to finish. So no, I want to do this. I want to let it go all the way. That's the first epoch. The second epoch is coming up. This is testing on the validation set. So it's the first epoch, 0.20. Error rate is now 0.11. Now it's 89% accurate. It'll get better and better as we go. So I can train it. I can save it. This tells me where it's going to be saved. If I save it, it's going to be saved in models, weights only path. I'm not really sure where that is. So let's go find out. There it is, models. It'll be under models, weights only. Back to here. I'm going to let this finish. Well, it's going to take a while. And once it finishes, now I really wish I wasn't doing it for, well, I'm on the third epoch now, 0 first. We're roughly halfway through. All right, while it's running. And so remember, the bits that matter here are, well, you have to figure out, you have to get your data. You have to load your data into a data loader. No worries. If you have a data frame that you can use, then you can create an image data loader from data frame, or if you just have if you have a file system with all your images on it and all the images are under directories that correspond to their labels, you can get it from a folder as well. There's several other ways to load these images. So there's a lot of factory methods to make this really easy and very flexible for loading your data. One call to set up your image data loader. One call to create your model once you decided on which model to use. One call to train your model. That's basically 3 lines of code to train a deep learning model. All right, so now it's roughly 92% accurate. I'm on the 4th epoch. It's going to run for a little bit. Now I'm going to want to generate my submission. So it says here, and I'm pulling a lot of this from this First Steps Road to the Top notebook. I want to look at my sample submission. So if you go and look at, what was in notebooks? Where's my notebooks? 95 code. It's in there. Models, test image, train images. Did I set this up so I can only see? Project. What's going on here? Change directory. Notebooks, ls-la. Code, project 4. I don't need that. Okay. Oh, for some reason I'm not picking up. I think I turned off. I did something to turn off showing all the other files in here. Because inside of PCSE 9595 code, I've got this submission.zip as well and submission.csv. And this just shows you what the output should look like. Let's go back here and see where I am for training. I'm almost done with the fourth epoch. So I'm on the training set, and it's about to go through the validation set. There's 33, just 33 batches in my validation set. Error rate's still dropping. Validation loss is still dropping. Go for one more, just one more epoch of training, which in an epoch is going through your data once, showing it to the model. The model adjusts its weights to predict the output, and the output just gets more and more accurate. My model now is, roughly 95% accurate. And that's pretty good. 95.8% accurate. That's pretty good. And so once it finishes this epoch, we can generate a submission. Now, if you go to the, and I'm looking over here, I'm not using much memory. My utilization is still fine. And you worry about this sort of thing for running out of memory. So if you're using some of the latest stuff like Stable Diffusion or any of the large language models, Stable Diffusion, you can run on a minimal GPU of 16 gigabytes. You can get away with that. But you can very easily use up all of your GPU memory. And if you use all of your GPU memory, you just get an out of memory error. There's not much you can do at that point. There's some things you can do to conserve memory. But if you do these things to conserve memory, something like called gradient accumulation, what that does is it increases the amount of training time slightly, but it lets you, do things like get by with smaller GPUs to train some of the larger models. But you need to have a GPU that will at least fit your model. Now we're almost finished. We're going to get the final result for this. I'm going through my training epoch, finishing all my training data. 80% of the data is for training. 130 batches are for training. And I'm about to go to the validation set and run through the validation set. And my validation loss is still dropping. My accuracy is somewhere around 93. What is that? 94%, 94.5%. So what that means is this model is almost always accurate when it predicts what kind of disease is occurring with the rice. All right, that's good enough. Now that since the validation loss is still falling, I would probably fine tune it for a few more cycles, but I'm not going to. This is good enough. So what I want to do now is I want to take a look-see. First off, I'm going to save my model because then I can just reload my model if I want and then run inference on it. My model's been trained. Now what I want to do is look at my sample submission. Now, is that there? Yeah, it is. It's just not showing up over here. I'm not sure why. Let me go up one. Go up there. And that's in notebooks. All right. There's my sample submission.csv. Now, here are all of my image IDs. Now, if you look inside of the test images, folder, and I'm going to go and look inside of there. So change directory, notebooks / code ls. So I'm going to look at my test images. All right, those are all my test images. So I've got a bunch of these things in there, and I can see how many there are. So I'm going to take ls-la, all of these lines that go to it, and then I'm going to pipe it to a program called word count, and I'm going to get the number of lines that it sees. This tells me I've got 3472 lines. If I go up here, you can see I have 33,472 test images. I have no idea what these are. There's no indication whether they're blast, they're normal, they're blight. I have no idea. I'm supposed to guess that using my model. Here's what your sample submission is supposed to look like from Kaggle. You've got your image ID and you've got your label that you've got to give. The image ID, notice these start from these are actually sorted. All right, 3469 rows by 2 columns. How many did I see here? There's 3472 rows. That's because I have, if you go all the way to the top, there's a dot and a dot dot. So that adds to, and there's one other row that it counted. So there are really 3469 images here. All right, so I've got my sample submission. So what I'm going to do is first load my test files, and I'm going to use this other FastAI function. I'm going to get all of the image files from tester, and the tester is defined up here as /test images. And I'm going to sort them. And then I'm going to create a data frame from that. And I think I'll be able to show you this, data loader from that. And so there's my test data loader. I get all my list of my test files. I give those test files to my data loader. And now I've got this iterator that will iterate through all the test files. And what I'm going to just do is take my learner, the learner that I just trained up here, there, that I trained right here, that's pretty good at recognizing what these diseases are. And I'm going to get the predictions given all of these images. I'm going to decode, I don't know what decoded output is. So let me run this. So I'm going to get probabilities. I'm not sure what learning get prediction returns. Get predictions, returns a tuple, get the predictions and targets on the DS, IDX, DH set optionally. Where's the return? I can do this. Escape above. Can I get this? Let's see if that works. Get the predictions and targets. With loss. Here's the source code. Get preds. I don't know what it returns though. Return tuple result. What's the result? CBL tensors. I'm not really sure what the output's going to be though. Well, it returns a tuple, but it doesn't tell me what's in the tuple. Maybe it does somewhere. I know I get the predictions, probabilities. I know I get the targets, but there's something else inside of the tuple. No, I don't know what it is. That's what this underscore is. So I'm not going to look at that. So let me see what and this is what the target, those are the probabilities and those are the targets. Now, when you do this, now it's running through all 3,000 of those images, sending all those 3,000 images to my learner, and the learner is making a prediction. Hey, this is normal. Hey, this is blast. That's what I'm getting back from it now. Okay, it's done. Now, indexes is there's one index, one number here for each of the images. So what are these numbers? Well, this is an index into a list of the potential, what types they could be. What is that list? What do they correspond to? Well, look at the vocabulary. So the data loaders that I passed in, here's my vocabulary. 0 is leaf blight, 1 is leaf streak, 2 is panicle blight, 3 is blast. So this one here, this 1 is bacterial leaf streak. So all I need to do is map these numbers to these actual disease types, because that's what it wants. That's what the submission wants. And so I'm going to create a mapping. Now I've done this. If you took data 301, you've done this already, where you just take a dictionary, and you can see this. Let's see, mapping. This is going to be a dictionary. 0 is bacterial leaf blight, 1 is bacterial leaf streak. And what I'm going to do is substitute. Every place I see a 0 in my indexes, I'm going to substitute bacterial leaf streak. Every place I see a 1, I'm going to substitute, 0 is leaf blight, 1 is streak, 2 is bacterial panicle blight. I'm just going to do a substitution. That's what I'm doing here. So I'm going to take a series of those indexes. I'm going to convert it to a series. So I'm going to have a series of all of these numbers, and I'm going to map this mapping to it, this dictionary to it. And that's going to convert those numbers to these values. And so this is what I get. For every one of those 3,469 images, I've got a prediction. This one, this one, this one, this one, this one. Now I sorted them. So this is for the very first image in my test images folder. All right, so I'm going to take this, these results, and I'm going to paste that label onto my original. Where's SS? Where did I define it? I defined it up here. Okay, here. Okay, so that's my submission sample. So for each image ID, I'm going to put the label in here. So image ID 20001.jpg, I'm going to substitute its label in. And that's what I'm doing here. SS label equals results. And so now if I look at my submission file, it's going to look like this. Image ID label, Kaggle requires that. For this particular image, my model said it's HISPA. This particular image, normal, and so on. And now I'm going to load it up to Kaggle. Kaggle tells you how you're supposed to format it. So you can read the data formatting in the submission requirements. And they say, well, format it this way. You want to have a CSV file that first row has image ID, comma, label. Second row, and from then on, all of your test images are sorted, low to high, then a comma, then what your model thinks that it is. All right. So I'm going to zip up submission.zip because I saved submission.zip here. And I'm going to submit this to Patty disease classification, this particular competition. And so if I do this, if I run this, it's updating it. I'm unauthorized. So that means my Kaggle key, let's see, here. Okay. I thought I updated that. Okay, so .kaggle, okay, change directory. I should have kaggle.json. Oh, that was created July 19th. That's pretty old. rm kaggle.json. So every time you get a new Kaggle key, it seems like I think I have to go to settings, API, create new token. It's going to download it up here. Let's show it in folder. It's in one here. Okay. Rename Kaggle.json. Because oh shoot. Okay, I'm going to delete that. Rename that. I always forget how to deal with space characters right there in Linux. Okay, I want to rename that. And now I'm going to go back to here. And I guess from here, I want to upload Kaggle.json. And it should appear here. I've done something to not show in my notebooks. I've done something so it doesn't show anything but folders. Okay. Change directory notebooks. -la. There's Kaggle.json. What I want to do is I want to move Kaggle.json I want to move it to /root /.kaggle. Let's see if that works. Change directory .kaggle. I think what happened was my key had just expired. All right, so let's see if this works now. All of this to get this to work. Updating. Okay. Oh, okay. I need to do chmod 600 on my key. All right, it submitted it to Patty Doctor. If you go up here, go to the Patty Disease Competition. You can go to, let's see, submissions. Where's my salute? Successful. Oh, here it is. Here it is, submission.zip. Completed after deadline 21 seconds ago. My private score, there's two scores. You get a private score and a public score. So I'm 0.94% accurate. So the public scores, when you submit stuff to Kaggle, what it will tell you is how good you're doing. So they'll test your stuff on a data set that they have. Once the competition's over, they'll take your, they'll run it, test it on a private. They'll take in this case, they're going to take a subset of the data and generate a private score. I think that's how they do it for this one. And so 0.94, I'm thinking that's pretty good. So, but if I look at all of them, I don't want just mine. It's just showing me mine now. Successful, recent. Those all of mine. Let's see, discussion, leaderboard. Okay, let's go look at the leaderboard. Here's mine. Jump to your leaderboard position, and I'm not going to be able to find it. The best scores were 0.98. So I'm going to be, right now, there's 608 more. Keep going down. So I'm looking pretty bad right now. Keep going down. 97. 94. Okay, I'm somewhere around here, somewhere in these 94s. Roughly middle of the pack. But there's some other stuff I could do here. For one thing, I didn't use that extra data here. If I wanted to increase my score, what I'm going to do is use this extra data, this variety and age. That's going to require a much more complicated model. And also what I would want to do is I want to go down to this model, and I'm thinking, hey, this model that I trained is pretty good. So why not train a couple of more models and then have all three of the models make a prediction and take the consensus estimate, consensus choice. So, but what I'm not going to do is I'm not going to do another ComNext Tiny model. I'm going to do a model from a different family completely, assuming that it's a different architecture. So I'll go here, I'll go down. If I was going to do that, there's a ComNext Tiny. All right, that's okay, but it's not really what I want. How about if I do this Swin S3 Tiny? So I'll do a ComNext Tiny. I'll train a Swin Tiny. And maybe I'll do a VIT Small. All three of these. Train three separate models, run three separate submissions, and then take the consensus estimate from all three submissions. Turn that in. That's going to kick my score up too. So the things that would really kick up my score are ensembling several different models, using this extra information here. And I think that would really push my score a whole lot higher. And what else can I do? There's some other, and I can do something called data augmentation. But is all of that is more appropriate to a course that's completely associated with deep learning. The takeaways are how to enter a Kaggle competition and effectively use deep learning to enter a Kaggle competition. You don't have to know everything. You have to know a little bit about it. You know how to you have to know how to look at your data. You have to know how to load your data, which is, let's see, the DataLoader for Fastai. It's a DataLoader. You have to know how to choose a TIM model, which I've talked about quite a bit. You have to know how to train a model, and you just keep training it as long as the validation loss keeps dropping. Then you have to figure out how to upload your solution. And that's it. This is one of the easier Kaggle competitions. But for Kaggle, the big problem you're going to run into is getting started. This notebook gets you started. And that's it. That's all I wanted to talk about in this class. And with that, you guys have any questions?
So does training for longer just give you a better score, or I don't know?
Let me go back. Let me go back to where we're training. Train the model. Maybe, as long as your validation loss keeps dropping, you can keep training. You're wanting to look at the validation loss. If the validation loss gets better and better and better, that means because you're training on this train data. Your train data is training loss is always going to drop. As long as your validation loss is dropping, that means your model is able to generalize from what it learned in the training session to the validation data set. So as long as this is dropping, you want to keep training. As soon as it starts going up, then you want to stop training. Now there's some fuzziness about the train and validation because to some extent you're fitting to your validation set in this case. So for training, you train as long as sorry, the validation loss keeps dropping. There's been a mosquito flying around tonight. I think I just swallowed it better than it biting me. There's some other things you can do with validation losses. Now, this is anathema to your deep learning classes. But in a lot of cases, what's going to happen is you've got this training, you're training on the training set, and you're testing on this validation set, and you're doing inference on the set of unknowns. What you could do is train this like this until your validation loss starts going up. Then what you could do, if you want to do well in Kaggle, you can think, well, I just really want to do well in this competition. So why don't I try this? Why don't I use all of my data for training? And I'm going to train it for the same number of epochs that I trained when I had a validation set, the same number of epochs that I trained for before the validation loss starts going on, but I'm using all of the data. And then I want to do inference on my unknown data, these test samples here, these test images, and then see what happens. So there are lots of tricks you can play with Kaggle that you will not play in the real world. But you can play these tricks for a Kaggle, use these tricks in a Kaggle competition by treating their test submissions sort of as, that's your validation set. Because Kaggle is going to actually run statistics on your validation set to tell you how good it is. So, which means that depending on what you do, you can use all of your training data to train your model. That's going to fly in the face of what you learn in your deep learning classes. What you can't do in that case is then you can't say how accurate in general or what the performance of your model is because you don't have a validation set. But It's a Kaggle competition. You're using Kaggle to tell you what the performance of your model is. Do you guys see the distinction there? You'll only do this in a Kaggle science competition. You'll never do it in the real world, just in a Kaggle, a data science competition. And it's all about eking out that last bit of performance. So any other questions on this and training and data loaders and whatnot?
I have a question. So in this competition, have you tried using like the slower, more accurate models and like an ensemble model? And like how high accuracy did you get?
I've tried for this particular competition. What I did was I wrote everything in PyTorch, and what I wanted to do was I wanted to compare Fastai to my PyTorch models, and I used this information here, and this pushed me up to around 96, 97% accuracy, and that's about as high as I got. I never ensembled anything, but if you follow this series of notebooks, and these are notebooks. Gosh, where did I? Here, this road to the top, part 1, part 2, part 3, part 4. If you follow these notebooks, you can see where Jeremy Howard, who wrote Fastai, actually writes submissions for this competition. In the end, he gets to, I think, roughly, where's the competition? Patty disease. Okay, leaderboard. He gets to roughly 98.963, 98.847. This is about as good as you're going to get. And a lot of these, you see these ones that are so close to each other. What's happening with these is essentially they probably got a good initialization on their model. There's very little difference. There's they've got one or two images right over their competitors. So this is about as good as you can get. And you can see somewhere down in here, if you're ensembling and you're using all that extra information, let's see if I can find. Yeah, here's his highest score doing that. 98.732. Looks like he's rated 25th on this. So yeah, this will work. This will work well. All of these techniques. But just using a simple model, one simple model, that gets you to 94% accuracy. And outside of a Kaggle competition, that's almost always going to be good enough for what you want to do. That extra 8% accuracy that you're going after, that's going to take you an extra few days worth of work to get to. So the difference is that those 3 extra percentage points on a job you're doing for a particular company, is that going to be worth it? That's a call you have to make. Kaggle competition, yeah, people win by hundreds of a percent. Real world, no. Real world, you can just probably use a simple model, but make sure you choose a model smartly. Choose something that trains fast, that converges quickly, and it's accurate on a data set that you're trying to work with. Other questions? Okay, all done. So that's it for the